Okay, so are we ready to dive into this?
Yeah.
It's a deep dive into a book about these models, these differentiable models.
Yeah.
And it's like, it's got this whole Alice in Wonderland vibe, but for like machine learning.
Mm-hmm.
The author even calls it a differentiable wonderland, which I kind of love.
Ah.
And get this, right? The author says they found that simple things, like really basic tasks,
Right.
was surprisingly difficult to do in this wonderland.
Yeah. Yeah.
But recognizing cats was like almost too easy.
Mm.
So this whole deep dive, what we're going to be doing is kind of uncovering those kinds of like weird twists and turns.
Yeah.
Unexpected things, right?
All right.
Especially since this book really focuses on the design of these models and like what they're made of.
So what's fascinating is that this whole differentiable wonderland the author talks about, it's everywhere now.
Yeah.
Whether we see it or not. I mean, think about it. Drones, self-driving cars, even designing new molecules, or those recommender systems that, seem to know what we want before we even do.
It's kind of creepy sometimes.
Yeah, it is a little creepy. All that is powered by neural networks. And what's even crazier, I think, is that training these AIs is getting ridiculously expensive.
Oh, it's insane. The amount of data they need, the processing power, the sheer size of these models, it's just it's mind-boggling. But like, how do they actually learn?
Yeah.
I mean, the book talks about supervised learning, but what does that actually mean, like in plain English?
So think of it like you're teaching someone by example.
Okay.
Like if you want an AI to caption images, you show it a ton of pictures with descriptions, and then it starts to get the hang of matching the words with what it's seeing.
Yeah.
Or text prediction.
Right.
It learns to guess what word you're going to type next based on what you've already written.
That's pretty wild.
It is.
Yeah.
And this is even being used in medicine now to analyze x-rays.
Oh, wow. So that's where differentiable models come in.
Right.
But why does the book use differentiable models rather than just saying neural networks? Because those kind of seem interchangeable to me.
So there's a subtle but important distinction there.
Okay.
So neural networks, that term kind of draws a comparison to the brain.
Yeah, right. Biological.
Right. And that can be misleading because these models don't actually work like biological neurons.
Yeah.
Differentiable models really emphasizes the math behind it.
Okay.
Specifically that we can use calculus to adjust the millions of parameters that these things have to get them performing how we want them to.
So it's less about mimicking the brain.
Right.
And more about clever math tricks to find the best settings.
Yeah, exactly. And those settings are controlled by data that's stored in things called tensors.
Tensors.
Which are the building blocks of these models.
Okay, so it's what do tensors, what do they look like?
So you can kind of think of a tensor as a container holding all the information that the model works with. It could be single numbers, or it could be more complex multidimensional arrays.
Okay.
But they're essential because they let us process information super fast using specialized hardware like GPUs.
Okay, that makes sense. So the tensors are they hold the data.
Yeah.
But how do we actually find the best values for all those different parameters? It's it's like finding a needle in a haystack.
Yeah, so that's where gradient descent comes in,
Okay.
which is an algorithm that helps us kind of find those optimal settings. You can imagine trying to find the lowest point in a valley. Gradient descent is kind of like rolling a ball down the hill. It keeps moving in the direction of the steepest descent until it reaches the bottom.
That's a great visual.
Yeah.
But the book mentions it's not always that straightforward, right?
Right.
What if there are multiple valleys?
Yeah, so that's the challenge with most neural networks, right? They're what we call non-convex.
Okay.
Which means that they can have many of those valleys or local minima. So gradient descent might actually get stuck in one that's not the absolute lowest point.
Got it.
Which makes finding the best overall solution really tricky.
So even with gradient descent, we're not guaranteed to find the absolute best solution.
Not always. No, it's a complex problem.
Yeah.
And researchers are always working on new techniques to improve it and avoid those local minima traps.
So it's an ongoing process.
Exactly.
Okay, so we've got the tensors holding the data.
Right.
And then we have gradient descent, which is guiding us towards those best settings. But what about the data itself?
Yeah.
The book, it mentions things like data sets, loss functions, and generalization.
Yeah.
What do those actually mean?
So data sets, they're kind of like the fuel for these models. They're collections of examples that the model learns from.
Right.
So like labeled images for, image recognition or text paired with like sentiment for analyzing emotion.
Right, got it.
But it's really crucial that those data sets are like representative.
Yeah.
And don't have biases built in.
Right.
Otherwise, the model learns the wrong things.
So a data set of only cat pictures would make a really bad dog identifier.
Exactly. And then there are loss functions. They're kind of like scorekeepers. They measure how well the model's performing.
Okay.
A common one is like squared error, which basically calculates the difference between the model's prediction and the actual value. The lower the score, the better the model's doing.
So during training, we're tweaking those parameters with gradient descent to try to get the lowest possible score on the loss function.
You got it.
Okay.
And the whole goal there is to achieve what we call generalization.
Okay.
Which means the model can perform well on new data it hasn't seen before.
Right.
Not just, the examples it was trained on.
So it's like if it aced a test on cats.
Right.
But then it can't tell a dog from a squirrel.
Exactly.
Not generalizing well.
It's not generalizing well.
Maybe.
So it's like a student who can only, parrot back what they memorize,
Right.
but they can't apply the concepts in a new situation.
Right. You might get an A on the test, but you're going to fail in the real world.
Exactly. That's why generalization is so important. We want models that can actually solve problems, not just like memorize in the data set.
Okay, that makes sense.
Yeah.
But what about the different types of models themselves?
Yeah.
The book starts with something called linear models, and then it kind of like quickly points out their limitations.
So linear models, those are things like linear regression.
Okay.
They're pretty simple, but they're also pretty limited.
Right. Yeah.
They assume, a straight line relationship between variables, and that's often not how the real world works.
Right.
Like if you think about like predicting someone's credit score based on their income, a linear model might say like, oh, higher income always equals a better score, which we know just isn't true.
No. So linear models, they're good for understanding the basics, I guess.
Right. They're a good starting point.
But they're not really powerful enough for most real-world problems.
Exactly. And actually, the book uses what's called the XOR data set to really illustrate this point. It's a classic example that shows even with just 4 data points, a linear model can't capture this very simple nonlinear pattern.
Got it.
It's like trying to fit a square peg in a round hole.
So linear models are out.
Right.
What's next? What's on the menu? The book goes into fully connected models.
Yes.
Also known as multi-layer perceptrons.
Yeah, MLPs.
Which sound a lot more complex.
They are more complex.
Okay.
And that's a good thing.
All right.
They overcome those limitations of the linear models by stacking layers of these interconnected neurons.
Okay.
And that allows them to model those nonlinear relationships.
So more layers means more power to get those complex relationships.
Yeah, it's like adding more layers of processing
Right.
to really capture those intricate patterns.
But how do they actually achieve that nonlinearity? I mean, isn't it still just using math at the end of the day?
Right. So that's where activation functions come in.
Okay.
These functions actually introduce nonlinearity into the model.
Okay.
So they allow it to like bend and twist those straight lines that the linear models would create into more complex shapes. So it's like adding curves to a road.
Right.
It lets you navigate a more complex landscape.
So fully connected models with their layers and activation functions are a big step up from the linear models.
Right.
But they still need to be trained efficiently.
Yeah.
Especially with these like massive data sets. How do we handle that?
So that's where stochastic gradient descent, or SGD, comes in.
Okay.
It's a really clever way to speed up training by using what we call mini batches.
Mini batches.
Which are smaller chunks of the data instead of using the entire data set all at once.
I got it.
It's like taking smaller steps to reach your destination faster.
Okay. So SGD with mini batches helps us navigate that massive data landscape a little more efficiently.
Exactly. And then there are activation functions like the popular ReLU, which stands for Rectified Linear Unit.
Okay.
It's super simple. It basically sets all the negative values to 0.
So it's kind of like a filter almost, like it only lets the positive signals through.
Yeah, you could think of it that way.
But what's so special about that?
So that simplicity, it helps with computational efficiency,
Right.
which is really important when we're dealing with these massive models.
Yeah.
And it helps mitigate what's called the vanishing gradient problem.
Vanishing gradient?
Yeah.
That doesn't sound good.
No, it's not good. It's this issue that can happen where, during training, the gradients, the things that are like guiding that optimization process. Right.
They can get so tiny that the model just stops learning.
Ah, okay.
REC2 helps prevent that from happening.
So RELQ is like the hero
Yeah.
that keeps the training on track.
It is in a lot of ways. It's simple,
Right.
but it's a very powerful activation function. It's become, a cornerstone of modern neural networks.
All right. So we've covered a lot of ground.
We have.
We've got tensors holding the data, gradient descent, which is guiding us towards the best settings.
Wow.
We've got linear models. We've got fully connected models.
Yep.
SGD, mini batches,
Wait.
now ReLU.
Right.
But how does all this magic actually happen behind the scenes?
Right.
The book brings up something called automatic differentiation.
So automatic differentiation, or AD, that's really the engine that makes training these complex models possible.
Okay.
Like, you have this super smart calculator
Yeah.
that can just figure out all those gradients, all those complicated functions that we were talking about.
Right.
It does all the heavy lifting. That sounds incredibly useful.
It is incredibly useful.
I can't even imagine, like, trying to calculate those gradients manually.
Yeah, it would be a nightmare.
Yeah.
Thankfully, we have AD to handle that.
So AD is kind of like the secret weapon that makes this all possible.
Yeah, it's a crucial ingredient for sure.
Okay, so we've got AD. Now we got to get back to the models themselves. We talked about the fully connected models.
Right.
But then the book moves into convolutional layers, which are apparently great at image processing.
Yeah, so convolutional layers, they're really specially designed to work with images.
Okay.
With the spatial structure of images.
Right.
So recognizing things like edges, textures, patterns.
Right.
It's kind of like how our eyes process visual information.
Okay, yeah.
But instead of light, they're working with data.
Data, yeah.
Yeah.
So instead of just treating the image like a bunch of pixels,
Right.
convolutional layers can actually, understand the spatial relationships between those pixels.
Exactly. And one of the key properties there is something called translation equivariance.
Translation equivariance.
Yeah, fancy word.
Yeah, what does that even mean?
So it means that if an object in the image moves, the convolutional layer can still recognize it.
Okay.
So it's not just looking for a specific pixel pattern.
Right.
It understands the object even if it changes position.
So it's not just looking for a cat in the top left corner.
Right.
It's understanding that that's a cat.
Right.
Regardless of where it is in the picture.
Exactly.
That's amazing.
Yeah.
So that's the power of these convolutional layers.
Yeah.
They're good for image recognition, obviously.
Yeah, object detection and a lot of other image-related tasks.
Convolutional layers sound pretty awesome for images.
Yeah.
But what about scaling things up? I mean, we talked about these huge data sets, these complex models.
Right.
Does it all still work when you push it to those limits?
So scaling up those really deep networks, that requires some special techniques. So one of those is data augmentation,
Right.
which is a clever way to kind of artificially expand the data set.
Okay.
So we do that by making little changes to the existing images.
Right.
So we rotate them, we flip them, we change their brightness.
Okay. They're basically making new variations of the same images.
Yeah.
To make the model more robust, to prevent it from just
Exactly.
memorizing those specific examples.
Exactly. It's like showing the model different perspectives on the same object.
Okay.
So it can generalize better.
Got it. What about regularization?
Yeah, so regularization.
The book mentioned that as another way to keep things in check when you're scaling up.
Yeah, so regularization techniques are all about preventing what we call overfitting.
Okay.
Which is when the model gets too good at memorizing the training data.
Right.
But then it fails to generalize to new data.
Right.
So it's adding guardrails to that learning process.
Right.
Prevent the model from going off track.
So it's making sure the model learns the underlying concepts, not just the specific examples it was trained on.
And there are various techniques for that, but one common one is dropout.
Okay.
Which is where we randomly deactivate some of the neurons during training.
Really?
It's forcing the model to learn more robust features.
So we're introducing a bit of chaos.
Yeah, a little bit of controlled chaos.
Interesting.
Yeah, and it's surprisingly effective.
Wow. Okay, so data augmentation, regularization, those are essential tools for, keeping these deep networks in line.
Right.
But the book keeps going. It introduces something called transformers.
Yes.
which apparently have like revolutionized so many areas of AI.
They really have. Transformers are really a game changer.
Okay.
They were originally designed for natural language processing, but now they're like dominant in like all sorts of areas. Yeah. What makes them so special is this attention mechanism.
Attention mechanism. That sounds familiar. Remind me.
Yeah. So think about how, like, when we read a sentence, we focus on certain words to understand the meaning.
Right.
Transformers kind of do something similar. They can selectively attend to specific parts of the input data, and they kind of ignore the irrelevant information.
Got it.
And that makes them really effective for processing sequences of data, like text or time series.
So it's like the model has this like spotlight that it can shine on the most important parts, making it more efficient, more accurate.
And this attention mechanism, it's led to a lot of breakthroughs.
Really?
Yeah, like machine translation, text summarization, and a lot more.
Wow, okay. Transformers and their attention mechanisms sound pretty revolutionary.
They are.
What other types of models are there? The book goes into graph neural networks, GNNs.
Yes.
What are those all about?
So GNNs, they're designed to work with data that's structured as a graph, which is basically like a network of nodes connected by edges.
Okay, like a social network.
Exactly, like a social network.
Right, where each person's a node. And then...
Right, and the connections are the edges.
Okay, got it.
Exactly.
So you can use these GNNs to analyze, like, social networks.
Yeah, or any data that can be represented as a graph.
Okay.
Which is surprisingly versatile.
What else, like, what other applications?
You can think about molecules, where atoms are the nodes and bonds are the edges.
Oh, interesting.
Or transportation networks.
Right.
With cities as nodes and roads as edges.
Okay, so GNNs are kind of like a specialized tool for understanding relationships and connections between things. Okay, GNNs, that's another one. What about recurrent neural networks?
Yeah, so recurrent neural networks, or RNNs, they're designed to handle sequential data, like text or time series or audio. And they do this by maintaining a memory of previous inputs. Which allows them to kind of capture dependencies and patterns over time.
So instead of treating each input as like independent, RNNs can actually understand how the inputs relate to each other.
Exactly.
Over time.
Yeah, it's like a model that can remember the past.
That makes sense for things like natural language processing.
Right, exactly.
Where, you know, the meaning of a word depends on what came before it.
Right, or time series analysis where the current value depends on previous values.
Yeah, okay.
Makes sense.
Are there any, like, challenges with RNNs?
So one challenge is that vanishing, exploding gradient problem that we talked about earlier.
Right. So RNNs can struggle with, like, those long-range dependencies.
Yeah, where information from earlier inputs needs to be carried over many time steps.
So even RNNs have their limitations.
Yeah.
Right? So it's an ongoing evolution of all these different models, each one kind of building on the last.
Right.
Okay, we've explored a lot just in this first part.
We have.
I mean, we've got these basic linear models all the way to these complex things like transformers, GNNs, and RNNs.
Right.
It's like we've taken a whirlwind tour of the differentiable wonderland.
We have.
And this is just the beginning.
Just the beginning.
So before we get ahead of ourselves, let's just take a moment to kind of like digest all this information. We'll pick up where we left off in part 2 and explore how these models are actually trained and deployed in the real world.
Yeah, sounds good. I'm looking forward to it.
Me too. I'm fascinated.
Yeah.
Okay, so I'm still trying to wrap my head around all those different model types we talked about last time.
Yeah.
But now I'm kind of curious, like, how do we actually build and train these things?
Yeah.
Especially those super complex ones. I mean, we touched on data augmentation and regularization, but is there more to it? The book mentioned something called the ImageNet Challenge, which sounded pretty intense.
Yeah, the ImageNet Challenge was a big deal. It was this huge competition. They had to classify images from a data set of over 1 million images with thousands of categories.
Wow.
It was like the Olympics for these image recognition algorithms.
So it's like a proving ground for all these new AI models, right?
Yeah, exactly.
Did it lead to any like major breakthroughs?
Oh, absolutely. It really pushed researchers to come up with more sophisticated architectures, better training techniques. The winning models really showcase the power of these deep convolutional neural networks.
Right.
And it really sparked a wave of innovation in the field. The lessons learned from ImageNet, they still have a huge influence on how we develop AI models today.
So ImageNet was like this pivotal moment
Yeah.
that showed us what's possible with large-scale AI.
Right.
But let's bring it back down to earth for a second.
Sure.
How do we actually go about picking the right model for a specific task? It's not just about picking the biggest and most complex one, right?
No, you're right. Bigger isn't always better. Model selection is really about finding that right balance between complexity and performance.
Okay.
Sometimes the simpler model might do the job just fine, or even better even.
Right.
It all depends on the problem you're trying to solve.
So it's like matching the tool to the task,
Exactly.
not using a sledgehammer for every problem.
Right.
But how do we avoid going overboard with complexity? The book mentioned overfitting, which sounded like a bad thing.
Yeah, overfitting, it's a major pitfall. It's what happens when a model learns the training data too well.
Okay.
Like it's basically memorizing the examples
Right.
instead of actually learning the underlying patterns. It's like a student who crams for a test,
Right.
gets an A,
Yeah.
but then they can't actually apply the concepts to anything new.
So it's like mistaking memorization for understanding.
Exactly.
The model might perform great on the data it's seen before,
Right.
but then it completely falls apart when it's faced with something new.
Yeah, and overfitting often goes hand in hand with model complexity.
Yeah.
You know, the more complex the model,
Right.
the more parameters it has,
Right.
the easier it is to overfit that training data.
So it's like this balancing act.
Yeah.
We want a model that's complex enough to capture the patterns,
Right.
but not so complex that it just memorizes everything.
Exactly. And that's where things like regularization come in.
Right.
Regularization methods are kind of like you're adding constraints
Right.
to the model's parameters.
Yeah.
So it discourages it from getting too specific to that training data,
Right.
encourages it to learn more general patterns.
So it's like we're guiding the model towards a
Yeah.
deeper understanding,
Right.
rather than just like a superficial memorization.
Yeah.
It's like teaching the model to like think critically instead of just like regurgitating facts.
Yeah, that's a great way to put it.
Okay, so regularization helps us keep that complexity in check, but we also need to find the optimal settings for all those parameters, right?
Right.
The book mentioned hyperparameter tuning, which sounded pretty technical.
Yeah, so hyperparameters are kind of like the knobs and dials you can adjust on a machine to
Right.
fine-tune its performance.
Right.
So things like the learning rate or the number of layers in a neural network, finding the best hyperparameters is crucial for getting good results, but it can be a bit of an art and a science.
So it's not just about picking the right model, it's also about picking the right settings for that model.
Exactly.
It sounds like a lot of like experimentation is involved.
There's definitely some trial and error, yeah.
Right.
But there are also more systematic approaches.
Okay.
Like grid search or Bayesian optimization. It's an
Right.
active area of research.
Yeah.
And finding that right combination of model and hyperparameters is key to achieving like peak performance.
Okay, so we've got model selection, overfitting, regularization, hyperparameter tuning, all part of this like intricate dance of building and training a successful AI.
Yeah. It's a lot to keep track of.
It is.
Yeah.
But let's not forget about the data itself.
Hi.
Earlier we talked about data augmentation. But are there other things we need to think about when it comes to like the data that we feed these models?
Yeah. Data quality is super important. There's that saying garbage in, garbage out, and
Yeah.
that definitely applies to AI.
Yeah.
If your data is flawed, if it's biased or incomplete,
Right.
the model is just going to inherit those flaws. It's like trying to bake a cake with rotten eggs. You're not going to get a good result no matter how good your recipe is.
Right. So data is like the foundation of everything.
It is.
So we got to make sure that's solid before we even start thinking about models and algorithms.
Exactly. The book really stresses that, making sure your data is representative, it's unbiased, it's properly cleaned.
Right.
Any skew in the data is just going to lead to a skewed model, and that can have some serious consequences depending on what you're using it for.
Can you give me some like examples of common data issues?
Yeah, so one common issue is missing data.
Okay.
If your data set has a lot of gaps or missing values that can really throw things off,
Right.
then there's noisy data,
Noisy data.
which is basically data that contains errors or inconsistencies. So think typos, inaccurate measurements, maybe even like deliberate attempts to manipulate the data.
Oh, wow. So missing or corrupted data can really mess things up.
Yeah, it's like trying to solve a puzzle with missing pieces or pieces that don't quite fit.
Right, right. What if we have like limited data to begin with?
Yeah.
Are there ways to like make the most of a small data set?
Yeah, there are. One approach is called transfer learning,
Okay.
where we use a model that's already been trained on like a massive data set for a related task, and then we just kind of fine tune it on our smaller data sets. Like, well, we're giving the model a head start.
So instead of starting from scratch,
Right.
we're leveraging the knowledge that's already embedded in this pre-trained model.
Exactly.
It's like taking a shortcut.
Yeah, it can be a huge time saver.
Okay.
And it can really boost performance when you're working with limited data.
Right.
And then there's data augmentation, which we talked about before.
Right.
By creating new variations of those examples you already have,
Right.
you can really increase the size of that training data.
Right. So data augmentation is like
Yeah.
stretching that limited data as far as it can go.
Exactly. It's about being resourceful,
Right.
making the most of what you've got.
Okay. So data quality is key. And there are ways to work around those limitations, like, if you have a small data set. But now I'm curious about, like, the really cool stuff, the models that can actually create new content. The book mentioned generative models.
Yeah, generative models. That's a fascinating area.
It sounded like sci-fi.
It is kind of sci-fi.
Right.
They can create new images, they can create new text, new music, even videos.
Wow.
It's like having an AI artist.
I've seen some of those AI-generated images, and they're pretty mind-blowing.
Yeah.
How do these models work? What's the, like, magic behind the scenes?
So the book talks about several different types of generative models, each with its own strengths.
Okay.
One type is called autoregressive models,
Okay.
which generate content one piece at a time.
Okay.
They predict the next element based on what's come before it.
So it's like a model that can, like, write a story word by word.
Exactly.
Or compose a song note by note.
Yeah, they're good at capturing dependencies and patterns over time.
Right, right.
Perfect for tasks like text generation, music composition, even predicting stock market trends.
Okay. Autoregressive models sound impressive. What about variational autoencoders, those VAEs? How do they work?
Yeah, so VAEs, those are a bit more complex.
Yeah.
They involve learning a compressed representation of the data, what we call a latent space. It's kind of like creating a map of the data,
Okay.
highlighting the key features and relationships.
So we're like boiling the data down to its essence,
Yeah, exactly.
capturing the most important information in a compact form.
So VAEs learn to encode that data into this latent space,
Right.
and then decode it back to the original format.
Okay.
And by manipulating points in that latent space,
Right.
we can actually control the characteristics of what we generate.
So we can use VAEs to, like, explore variations of the original data,
Yep.
generate new examples that share the same underlying structure,
Right.
but have, like, different specific features.
Exactly.
It's like having a set of, like, knobs and dials to tweak the output.
Yeah, it's a good analogy. They're great for tasks like generating variations of existing images or maybe creating new molecules with desired properties.
That sounds really powerful.
Yeah.
Okay, VAEs sound cool. But the generative model that seems to get the most buzz are these generative adversarial networks, or GAN-ANS. Why are those so special?
So JANers, they're a unique breed. They involve training two neural networks in competition with each other.
Okay.
So one network, we call it the generator, that creates new content. The other network, the discriminator, tries to tell the difference between real and fake content.
So it's like this game of, like, cat and mouse.
Exactly.
The generator's trying to fool the discriminator, while the discriminator is trying to, like, get better at spotting the fakes.
And this back and forth competition pushes both networks to improve. The generator gets better at creating realistic content,
Right.
and the discriminator gets better at detecting those fakes. And you end up with some really realistic generated content.
So GANs are like this, like, crucible.
Yeah.
Where these two networks are battling it out,
Yeah.
and the end result is something, like, amazing.
Yeah, they've achieved some remarkable results. Generating photorealistic images, creating realistic videos,
Yeah.
even composing music that's hard to tell apart from human-composed music.
Okay. GANs sound like a potent tool for creating all sorts of new content, but are there any challenges with them?
Yeah, they can be a bit tricky to train. Finding that right balance between the generator and discriminator is really important.
Okay.
Sometimes the training can become unstable.
Right.
The generated content might be unrealistic or just bizarre.
So it's not just about, like, letting these two networks fight it out.
Right.
There's an art to, like, setting things up correctly.
It's an art and a science. But the potential rewards are huge because, Jans have this power to create these entirely new, realistic things.
Right.
And it really blurs the lines between what's real and what's made by a machine.
All right, so we've covered a lot on generative models. From these autoregressive models to VAEs and GANs, it's incredible how AI can now create this content that, rivals human creativity.
Yeah.
But let's switch gears for a moment and talk about how these models actually learn to understand the world.
Okay.
The book talked about something called representation learning.
Yeah, so representation learning, that's at the heart of how these models make sense of the world.
Okay.
It's all about learning these meaningful representations of the input data, capturing the essence of what's important, ignoring the irrelevant details.
So instead of just treating the data as, raw numbers or pixels,
Right.
representation learning allows AI models to extract meaning and understanding from the data.
Exactly.
Okay.
Transforming the data into a form that the model can actually work with, highlighting the important stuff.
Okay. Can you give me an example of how that works in practice?
Yeah, so imagine you're training an AI to recognize different breeds of dogs.
Okay.
Representation learning allows the model to go beyond just looking at the individual pixels
Right.
and instead learn to identify key features, like the shape of the ears, the length of the snout, the texture of the fur.
Okay.
Those learned features, they form a representation of the dog, and the model can use that to figure out what breed it is.
So it's like giving the AI a set of tools to dissect and understand the data
Right.
and focus on what's important.
Yeah, it's a good way to put it. And those learned representations are often much more compact
Right.
and informative than the raw data itself. So
Right.
it makes it a lot easier for the model to learn.
Okay, representation learning sounds pretty fundamental to how these models work.
It is.
But how do they actually learn these representations? What are the different ways AI models can, learn?
Right. So the book dives into different learning paradigms. And the most common one is supervised learning. It's kind of like you're teaching a student by giving them examples and telling them the right answers.
Right.
So you give the model these labeled data.
Okay.
Each example has a corresponding label or target.
Right.
And it learns to map those inputs to those outputs based on those examples.
So supervised learning, it's like you're giving the model flashcards.
Yeah, exactly.
With a picture on one side and a word on the other.
Yeah.
And then it learns to associate the picture with the word.
That's a great analogy.
Okay. Supervised learning has been super successful. We see it everywhere.
It has, yeah, like image classification, speech recognition, even machine translation.
Right. It's like the workhorse of AI.
It is. But it does have its limitations.
Okay, what are some of the limitations?
So one limitation is that it requires a lot of labeled data.
Okay.
And that can be expensive and time-consuming to collect. And sometimes it's actually hard to come up with clear, consistent labels.
Right.
Think about, trying to label the emotion in a piece of music.
Yeah, that's tough.
Yeah, it's subjective, open to interpretation.
Okay, so what are the alternatives then?
Right.
What happens when we don't have those neat labels to guide us?
So that's where unsupervised learning comes in.
Okay.
It's more like you're giving a kid a bunch of toys and letting them figure out how to play with them.
Right.
Without any instructions.
Okay.
The model gets this unlabeled data, and it has to kind of discover the patterns and structures on its own.
So it's about exploration and discovery.
Yeah.
The model has to find its own way without any,
Exactly.
explicit guidance.
Yeah. Unsupervised learning is great for things like clustering, where you're trying to group similar data points together.
Right.
Or dimensionality reduction, where we try to simplify the data while preserving its important structure.
So unsupervised learning could be useful when you've got these complex data sets where it's hard to come up with clear labels.
Right.
Okay, but what about learning through, interaction? The book also mentions something called reinforcement learning.
Right. Reinforcement learning, that's kind of like training a dog. You use rewards and punishments.
Go.
So the model or the agent learns by interacting with an environment.
Okay.
And it gets feedback, like rewards or penalties.
Okay.
The goal is for the agent to learn a strategy that maximizes its rewards over time.
So it's like trial and error. The agent learns from its mistakes.
Right.
And tries to, improve its behavior to get more of those rewards.
Exactly. Reinforcement learning has been successful in a lot of cool applications. Training agents that play games like AlphaGo, which beat that professional Go player.
Right. That was a big deal.
Yeah, it was a big deal. It's also used to train robots to navigate those complex environments, or maybe develop personalized recommendation systems.
Okay, so reinforcement learning sounds like it has like potential for a lot of applications.
Yeah.
Especially when it comes to training agents that interact with the real world.
Right.
But let's go back to something we touched on earlier, deep learning. What is deep learning, and why has it become so popular?
So deep learning is really a subfield of machine learning. It focuses on deep neural networks, which are these models with multiple hidden layers.
Right. So it's all about those layered structures we talked about earlier.
Exactly.
More layers means more power to capture those complex patterns.
Exactly. And they've been incredibly successful in like image classification, object detection, natural language processing, even machine translation.
Yeah, so what's driven this recent success? I mean, why is deep learning taking over the AI world?
So a few factors have kind of converged here to make deep learning so powerful. One is just the availability of massive data sets. I mean, deep learning thrives on data.
Right.
And we just have this explosion of digital data in recent years. And that's the fuel for these models.
So data is still king in the AI world.
It is. But data alone isn't enough, right? We need the computing power to process it.
Right.
And that's where advances in hardware, specifically GPUs, those have played a huge role.
GPUs, yeah. So those are those specialized processors that can handle the massive computations required for deep learning.
Right, exactly. They speed up the training process significantly.
So it's like a combination of the data and the hardware that's like unlock the power of deep learning.
Yeah, and then there's also the algorithmic innovations themselves. New activation functions like ReloU, new architectures like convolutional neural networks and transformers.
Right.
Those have pushed the boundaries. It's a very dynamic, rapidly evolving field. New breakthroughs happening all the time.
Deep learning sounds amazing. Are there any like downsides?
Yeah, I mean, there's no such thing as a free lunch, right?
Right.
One challenge is what we call the interpretability of these models, these deep neural networks.
Right.
They can be really complex and opaque.
Okay.
So it's really hard to understand why they make certain decisions.
So it's like we have this black box.
Yeah.
It spits out accurate results.
Right.
But we don't know how it got those results.
Yeah, exactly. And that lack of interpretability can be a problem, especially when you're talking about like medical diagnosis or making decisions that affect people's lives.
Yeah.
We need to be able to understand how those decisions are being made.
Yeah, to make sure they're fair.
Right.
Unbiased.
Exactly.
Okay. So interpretability is something to think about. What other challenges are there?
Another challenge is the data efficiency of deep learning.
Okay.
These models often need huge amounts of data to train effectively.
Right.
And that can be a big problem when you're working with domains where data is scarce or it's expensive to collect. Think about like rare diseases or like specialized scientific research. You might not have millions of examples.
So deep learning's like data hungry.
It is.
And that hunger can be a problem when data is limited.
Right.
What else?
And then there's the issue of robustness.
Okay.
Deep learning models can be a little brittle.
Okay.
Meaning they can be easily fooled by small changes in the input.
Okay.
So think like a self-driving car
Right.
that gets confused by a sticker on a stop sign.
Oh, right. Or like a facial recognition system that misidentifies someone because they're wearing a hat.
Exactly. So robustness is about making sure these models can handle the unexpected.
Right.
They can perform reliably in real-world situations.
Yeah, so they don't just fall apart when they encounter something new.
Right.
Okay. So we've covered a lot of ground on deep learning.
We have.
We've talked about the architecture, the capabilities, the challenges, the limitations. It's clearly a powerful tool, but it's important to use it wisely.
It is. It's one tool in the AI toolbox. There are many other approaches and techniques out there.
Right. Well, I'm definitely starting to get a better understanding of how all these pieces fit together.
Good.
I think we need to take another break.
Okay.
Let all this sink in.
Sounds good.
But when we come back for the final part of this deep dive, I'm hoping we can explore some of the broader implications of AI. Things like the ethical considerations
Right.
and the role of humans
Right.
in a world that's increasingly driven by AI.
I'm looking forward to that.
All right. See you soon.
See you soon.
Okay, so we've gone pretty deep into all the nuts and bolts of how these models work, from those basic building blocks all the way to the mind-bending complexity of dance. But now I'm kind of curious about the bigger picture. Where's
Yep.
all this heading? What's next for AI? What's next for these differentiable models? The book hinted at some like pretty futuristic ideas like meta learning,
Yeah.
which
Yeah.
sounded like something straight out of a sci-fi movie.
Yeah. Meta learning, definitely one of the most like intriguing areas of research right now.
Okay.
It's essentially about teaching AI to learn how to learn.
Hey, wait, learning to learn.
Yeah.
That sounds kind of like a snake eating its own tail. How does that even work?
So the idea is you train a model not for a specific task,
Okay.
but to be able to adapt quickly to new tasks with very little data.
Okay.
So instead of being like a one-trick pony, a meta learning model would be more like a quick study,
Right.
able to pick up new skills really rapidly.
So it's like giving the model the ability to become a super learner.
Right.
Able to like master these new challenges with just a few examples.
Exactly.
That would be like a game changer.
It would be huge.
Wow. Are there any other areas of research that kind of have you excited about, like the future of AI?
Yeah, another area that's getting a lot of attention is neurosymbolic AI,
Okay.
which aims to combine the strengths of neural networks with symbolic reasoning. So it's like you're merging the intuitive pattern recognition abilities of those neural networks
Right.
with the logical, structured thinking of
Yeah.
more traditional AI systems.
So it's like bridging the gap between those two approaches.
Exactly.
What are the potential benefits of that?
Well, one of the really promising things is that neurosymbolic AI could lead to these systems that are not only powerful, but also more transparent, more explainable.
Yeah.
We might actually be able to understand how they make decisions, which, is crucial for trust and accountability.
Right. Right. We talked about that earlier, that interpretability problem
Right.
with the deep learning models.
Right.
So neurosymbolic AI could be a way to address that.
It could be, bring more transparency to AI decision making.
Yeah. And could this approach also lead to systems that are like more robust,
Yeah, that's the hope.
more adaptable, able to like handle these unexpected situations and like reason about the world in a more human-like way?
Exactly.
Okay. Meta learning, neurosymbolic AI, those sound like they could lead to some incredible breakthroughs.
Yeah.
We've also talked about some of the challenges like the interpretability, the data efficiency, and the robustness.
Uh-huh.
Are there any other like hurdles that researchers need to overcome as AI continues to evolve?
Yeah, one of the biggest challenges is just scalability.
Yep.
As these systems get more complex, more data intensive, we need to figure out how to train and deploy them efficiently.
Right.
We can't just keep throwing more data and computing power at the problem. We need smarter approaches.
So it's not just about building like bigger, more complex models.
Right.
It's about making them practical to actually use.
Exactly. Another challenge is ensuring that these systems are reliable and safe.
Okay.
As we start using AI in healthcare, transportation, and finance, the stakes get higher. We need to be sure that these systems are robust, they're reliable, and they're making decisions that, align with our values.
That's a really crucial point.
Yeah,
AI is becoming increasingly integrated into our lives,
it is.
and we need to make sure that it's being used responsibly, ethically.
I agree completely. We need to have these discussions about the societal impact of AI, develop some guidelines, some regulations
Right.
to ensure that AI is used for good and doesn't create unintended consequences.
All right. Well, we've covered a lot of ground in this deep dive.
We have.
We went from the nitty-gritty of how these models work to like these exciting possibilities and
Yeah.
these potential challenges on the horizon. It's clear that AI and these differentiable models, they're rapidly evolving. It's really hard to say where it's all going.
Yeah, it is. The field is moving fast, and there are a lot of open questions. But one thing's for sure, AI is going to continue to have a huge impact on our lives.
Right.
And it's important to stay informed and engaged in the conversation.
Absolutely. This deep dive has been incredible.
Good. I'm glad.
It's really given me like a much deeper understanding of AI
Yeah.
and its potential. But I think like the most important takeaway for me, and hopefully for our listeners,
Yeah.
is that AI isn't just a technological advancement. It's a human one.
That's a good point.
It's a tool that we can use to create a better world, but it's up to us to guide its development
Yeah.
and make sure that it aligns with like our values.
Well said. AI is a reflection of, our ingenuity, our aspirations.
Right.
And it's up to us to shape its future and make sure it serves humanity.
So as we wrap up this deep dive, let's remember that, AI is this powerful force.
It is.
And with great power comes great responsibility. Let's keep exploring, keep questioning, and keep working together to make sure AI is used to create a better future for everyone.
I couldn't agree more. Thanks for having me.
And thanks to all of our listeners for, joining us on this deep dive. We hope it sparked your curiosity and left you with, like, a sense of wonder and excitement about the future of AI. Until next time, keep learning, keep exploring, and keep pushing the boundaries of what's possible.